Okay, folks, we're working our way through the pre-work for section 2.6, and I want to, real quick, let's just revisit. In the last video, we gave the definition of continuous at a point, and let's just revisit that. We said that if the limit as x approaches a of f of x is equal to f of a, then we say f is continuous at x equals a, continuous. Okay, so we examined a number of these points. We said, oh, we're not continuous at -1, we're not continuous at 3, we're not continuous at 4, but we were continuous everywhere else on the graph of that function. So it's important to sometimes just give the layman's definition for something. Loosely speaking, and this isn't an entirely precise definition, but we can think of it. We can think of a function as continuous at a point if you can draw its graph without picking up your pencil at that point. So, for instance, looking at this function here, I can draw this segment from minus infinity to -1. I can draw that entire segment without picking up my pencil, so it's continuous on that interval. Okay. Likewise, all through here, I can draw the graph without picking up my pencil, but notice that at -1 or at 3 or at 4, in order to finish out drawing the graph, I have to pick up my pencil to continue drawing it. So that's why it's not continuous, or that's a visualization as to why it's not continuous at 4 or at 3 or at -1. And that gives some insight again as to why we were continuous at x equals 1, even though something interesting was happening there. The limit exists and the functional value exists, and they agreed with each other at x equals 1, so we're continuous at x equals 1. All right, so let's work through this. So one thing that we often do in math is we give a definition for a property at a particular point, and then we'd like to build up on that. So it turns out that if, let's suppose that we've got two functions and they're both continuous at x equals a. Well, then lots of other functions would also be continuous at x equals a. Specifically, their sum would be continuous. So remember the sum function f plus g of x. That function is continuous at x equals a, as is their difference. Remember the difference function looks like f minus g of x, and that's defined to be, as you would expect, you take the first function and you subtract the second function from it. Okay. What else? Well, so is their, what function is this? So is their product and quotient. What's the quotient function? Remember, the quotient function would look like f over g of x. That would equal f of x divided by g of x. So let's just recap. If we know that two functions are continuous at x equals a, so is their sum, their difference, their product, and their quotient. But be careful, as often happens in math, we have a caveat. We would not be continuous if g of a were 0. So this fourth property only holds if the quotient function is non-zero the denominator of this quotient function is not 0 at x equals a. Okay. Also, if we've got a continuous function, or if f is continuous at a point, then so is the function that is the constant multiple times that function. Okay, so I want to go ahead and just give you one brief proof of this, and you'll have to do a couple more of these in class, but let's prove that if I know these two underlying functions are continuous at a, then so is their sum. Okay, so let's take a look at that. I'm going to just put it on another page here. So what do we need to do? Well, our goal is what? Well, the definition of continuity says that if we take f plus g of x and we look at the limit as x approaches a, our goal is to show that this equals what? By the definition of continuity. So this is evaluating a limit. This is what we've been doing for the last 2 weeks. And our goal is to show that evaluating the limit there is the same thing as just evaluating the function at that point. Okay? So let's just, if we haven't said it explicitly, let's just go ahead and say so. When you know a function is continuous at a point, evaluating the limit of the function at that point is just the same as evaluating the function there. And so we'd like to show that, okay, suppose we know we're continuous at these two underlying functions, then how do we know whether their sum is continuous? And let's go ahead and take one side of this and let's show that. So we take the limit as x approaches a of f plus g of x. Okay. Well, this is the sum function, so let's just give its definition. That's f of x plus g of x. That's what it means to take to give the sum function. This is just by definition of the sum function. Okay. Now what can I do? Well, we had a property way back in section 2.3 that said this is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Which limit property was this? Well, this was the property that said the sum of the limits is the limit of the sums, or the limit of the sum. Okay, so this was a property we had. We said that limits distribute over the operation of addition. Well, what do we know this expression is equivalent to? Well, we assume that f is continuous at x equals a, so we know that this is equal to f of a. How come? Because to be continuous at x equals a says evaluating the limit is the same thing as evaluating the function at that point. Likewise, this is just g of a. Evaluating the limit as x approaches a of this function is the same thing as simply plugging a into the function. Again, that's only because we know that f and g are continuous at x equals a. Okay. Well, what is this function here? Well, this is just f plus g of a. So it's the sum function evaluated at a. And notice that we've met our goal. So fill in the box and say, yep, we did that proof. Okay. So let's jump back to the previous page. So next thing I want to say is that if f is continuous at x equals a for all values on some open interval, then we say that f is continuous on that interval. Okay. So this is a way of saying, okay, suppose f is continuous at a whole collection of points, then we can say that f is continuous on that collection of points. What we're doing here in math is we're taking what's called a pointwise definition. What does it mean to be continuous at a? And we're extending it to something larger. In this case, saying what does it mean to be continuous on an interval? Specifically, if f is continuous on the interval from minus infinity to infinity, that means take any value a on the number line, and if f is continuous there, then we're just going to call that function a continuous function. Okay. So, based on what we said above, if we've got two functions, f of x equals f of x is equal to x squared plus 1, and g of x is equal to sine of x, I'm giving you the fact that they're both continuous at 0. And that shouldn't surprise you if you look at their graphs. You can draw their graphs at 0 without picking up the pencil, right? So here's your x squared plus 1 function, and here's your sine of x function. I should do that in a different, I should have done this one in a different color also. And here's your sine of x function. Okay. And notice that I was able to sketch both these regions without picking up my pencil at x equals 0. And this is where x equals 0. Here, right here we have where x equals 0. So I was able to sketch the graph there without picking up my pencil, so I'm saying it's continuous there. Okay. Really what I'm saying is that evaluating the limit at x equals 0 is the same thing as simply plugging 0 into the function. Or evaluating the limit as x approaches 0 for the sine of x from either direction is the same thing as just evaluating the sine of 0. So my question for you is, what else would be a continuous function? Okay. Well, based on what we set up above, I've got two continuous functions. They're continuous at 0, so is their sum. So this function is continuous. Let's give it a new name. Let's just call it h of x is equal to x squared plus 1 plus the sine of x. This is continuous at x equals 0. What else is? Well, so is g of x let's not do g because it's a letter we've already used. So is, say, j of x, which could be the difference function, x squared plus 1 minus the sine of x, is continuous at x equals 0. Okay? So I've asked you to give me 5 new continuous functions and one that is not continuous. So I've already given you 2, and I'm simply running through these properties. The sum is, the difference is. Go ahead and look at what else you could possibly do to construct some continuous functions based on these two old functions. Okay, so pause the video, fill these out, and we'll talk about them in class, in the next class period. Okay, moving on to number 13, where is this function continuous? Well, notice that f of x could be thought of as the ratio of these two functions, where g of x is the numerator function, which is x squared minus x minus 2, and the denominator function would be x minus 2. So I could think of f of x as one continuous function divided by another continuous function. So notice that g of x is continuous where? Well, it's continuous on minus infinity to infinity. It's a continuous function. It's continuous everywhere. Same thing with h of x. So it's continuous on minus infinity to infinity. And why is that? Well, we're sort of cheating a little bit. We haven't actually said why these two functions are continuous. If you looked at their graphs are polynomials. So you can sketch those polynomial functions without picking up your pencil. Or you could use the direct substitution property if you wanted to just show continuity at any point here. But we'll sort of revisit that when we get to section 2.7. Okay? So f of x is comprised of the quotient of two polynomial functions. Both these polynomial functions are continuous on the real number line. Okay? So let me ask the question, where is f of x continuous? Well, we said that generally, if I wanted to construct a quotient function from two functions that I know to be continuous, that quotient function is also continuous. Be careful. As always happens with division, there's a caveat, provided that the denominator isn't 0. Okay? Well, notice that the h of x, the denominator of this function, will be 0 if x equals 2. So where is the original function? Where is f of x continuous? So f is continuous on the interval from minus infinity to 2, unioned with 2 to infinity. We'll talk a little bit more about what it means to be continuous on a set or versus on an interval.